Paper 184, Deep Unsupervised Anomaly Detection. This is a joint work by Tangqing Li, Zheng Wang, Siying Liu, and Wenyan Lin. Anomaly detection refers to the identification of patterns that do not conform to expected normal behavior. It is a critical task in diverse application domains such as fraud detection and surveillance video profiling. Fundamentally, an anomaly is something with insufficient similarity to the rest of the data. This similarity can be computed on the basis of some feature. However, what makes an ideal feature representation depends on what constitutes an anomaly. This forces it into a chicken and egg problem. The problem is made more challenging when the data is of high dimensions. Existing methods, one-class methods. Under this framework, a discriminative boundary surrounding the normal instances is learned. However, such techniques are often affected by the curse of dimensionality. Next, we have reconstruction-based methods. These methods assume anomalies are incompressible and hence cannot be effectively reconstructed from low-dimensional projections. More recent works, such as VAE and ADAL, use deep learning techniques. However, they require pre-isolation of normal data in the training phase. There are also density-based methods. They treat anomalies as no-density regions in some feature space. Unfortunately, they are less applicable on high-dimensional data, where density estimation is a challenge. Next, we present our system architecture. We obtain an initial split of the data into normal and abnormal subsets through distribution clustering. Clusters with low variances are hypothesized as normal candidates, while those with high variances are treated as abnormal. The normal candidates are then passed into an autoencoder for representation learning. Now, with the learned autoencoder for the whole dataset, all samples membership can be re-evaluated. The bottleneck feature set C is concatenated with the reconstruction error set R to form a new feature set. This new feature will be used as a proxy for clustering. The dimensionality of this new feature is now sufficiently low. We can apply traditional clustering techniques such as GMM to reselect normal candidates. The reselected normal candidates are fed into the autoencoder for representation learning, followed by membership re-evaluation on the whole dataset. This whole process is iterated till there is no change in the membership. Now let us take a closer look at distribution clustering. Here we show the clustering results for Cypher10 and MNIST, sorted by cluster variances. We see that clusters with low variances are more homogeneous, while those with high variances contain anomalous samples. For evaluation, we first test our algorithm on KDDCUP, a typical benchmark. On the left is the ROC comparison on unsupervised methods. With DHEMM, there is state-of-the-art, and OCSVM a baseline. Our method outperforms both with notable margins. We also evaluated the three methods with increasing percentage of anomaly. As shown in the tables, both OCSVM and DHEMM are more severely affected by an increase in anomaly percentage, while our method remains robust. Next, we compare the AUROC scores and several datasets. For semi-supervised methods, we have OCNN and geometric transform. For unsupervised methods, we compared against DHEMM and OCSVM. On complex datasets such as Cypher10 and cat versus dog, our method has higher performance gain among all unsupervised methods. Our method is also on par with semi-supervised methods, although it does not use any label information. The last column presents results obtained using distribution clustering alone, showing its effectiveness at making an educated first guess. We also evaluated our method on UCF crime, a video dataset consisting of 13 crime categories. Despite being unsupervised, our method was able to achieve an average AUROC of 72.9%, losing just by a tiny margin of 2.5% to the state-of-the-art. On selected samples, we also plotted a segment-wise anomaly score against ground truth. The orange lines show the ground truth and the blue lines show the estimated anomaly score. Our method significantly outperforms DHEMM. Thank you for watching.